Hey guys, welcome again to the Maths Club. If you are just joining us, welcome. If you have not subscribed to our channel, smash that subscribe button on there. And if you go on to like the video, don't forget to click the like button under the video. So for some time, we're looking at set theory, and in this particular video, we're looking at set builder notation. We've mentioned set builder notation many times in the previous videos, so I think now is a good time for us to really focus on it and see what it is all about. Now, before we go there, there's some important symbols that we need to take note of. So while we're working in the set builder notation, there are some symbols that will be seen, and it's best that we are all on the same page in terms of understanding. So the first symbol that we're going to see is when you see Z, right? Z is a set of integers. So any integer that you see, either a negative value, a positive value, or a zero value, right? They all belong to the set of integers. And if you see this Z, is symbolizing that. The next symbol we're going to be talking about is the n, right? When you see n, we're talking about the counting numbers or the set of natural numbers. So if you're counting, you'll be counting 1, 2, 3, 4, 5, 6. So all those numbers that you count, you won't be counting minus 1, minus 2. No, you won't do that. So all those counting numbers belong to the set of natural numbers. If you see n, you know they're talking about set of natural numbers or counting numbers. If you see this e, this symbol that's like e is saying element of. So if you see maybe something e something, or if you see AEB in this E in this form, you know that A is an element of set B, right? Something like that. You see that when we move on. So when you see this U, I mean, this is familiar, right? This is the universal set. And less than or equal to symbol, greater than or equal to symbol. So that's it in terms of the important symbols that we need to know before we enter into the set builder notation. So what is the symbol of the set builder notation? You'll see something like this curly bracket. Sometimes you'll see something like this one that's telling me that x is an integer. This colon that you're seeing there is symbolizing the word such that. We're given a particular number or a particular variable, right? And then you'll be given the condition for that particular variable. So this x is a variable. X could be anything. When I mean variable, it could be anything. X could be 1, could be 2. So it's not a fixed number. It's a variable number, right? And I know that x is an integer and x is less than 7. So if they tell me that is an integer, that means anything less than 7 could be minus 5, minus 4, minus 3, minus 2, 0, 6, but not 7. Anything less than 7 and an integer is a member of the set A. So just like they said, A is a set of integers, x, and they said x is less than 7. So how do we call it in full? We say A is a set of integers, x, such that x is less than 7. Now let's see some examples regarding this set builder notation. The first example says that we should list the members of the set x such that x is greater than or equal to minus 2 and x is a member of z. Remember what we said about z? What did we say about z? We said z is a set of integers, negative, positive, or 0 or number values. So let's solve it together. So if this is the case that x is greater than or equal to minus 2, that means that it's going to include minus 2 because of this equal to. So we have minus 2, minus 1, 0, 1, 2, on and on like that. These are the members of our sets. Let's see if we're actually correct. Great, so you can see it's minus 2, minus 1, 0, 1, 2, 3. All numbers that are members of the set integer and are greater than or equal to minus 2 will be found inside these our sets. Let's have another example. This example is saying that given that x is an integer, we should list the members of the first set is x such that x is less than 6 and intersection x such that x is greater than or equal to minus 4. Let's solve it together. So if we were to break down this first set, I could break it down and say we could have values all, we don't know what is going to be. I mean, it could be minus 1000, minus 999, all of that. But let me just come to, let's say, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, and 5. We're not going to include 6 because it is less than 6. So this is like the elements of the first set. Now for the second set, let me just do an arrow here. We know that x is an integer such that x is greater than or equal to minus 4. So we're going to start from minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, 6. Let's just stop there. Now we have these two sets. They told us that we should find the intersection between these two sets. So what do they intersect? You agree with that we have minus 4 here, all up to the way of 5 and 5. So if I want to find the intersection between them, so if I say if this is my set A, intersection my set B, I could say this is what? Minus 4, minus 3, dot, 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 up to what? Up to 5. So if I find the elements of this set and the elements of these other sets, and I find the intersection between the two of them, you will see that it will be from minus 4 up to 5. Let's see if we're correct. Great, so you can see minus 4, minus 3, minus 2, minus 1 up till 5. Now this next example is saying if x is, well, remember what the symbol is? Great, element of. So if x is an element of the universal set, and the universal set contains numbers 1 up to 10, list the members of the following subsets of U. X such that x is an odd number, x such that x is less than 7, x such that x plus 2 is greater than or equal to 7, x such that x minus 2 is equal to 2, x such that 3x minus 2 is equal to 19, x such that x is a factor of 24. Let's solve it together. So for the first of them, x such that x is an odd number, the first odd number in these are universal sets is what? Is 1. Great. So 1, the next will be 3, next will be 5, next will be 7, next will be 9, next will be 11. No, because our constraint is stopping at number 10, right? Our universal set is stopping at number 10. Let's see if we're correct. Great, so we have 1, 3, 5, 7, 9. Now the next one is saying x such that x is less than 7. If you look at all our universal sets, what values they are less than 7? So we could say 1, 2, 3, 4, 5, and 6. So we should have numbers 1 to 6 in this particular set. Let's see if we're correct. Great, so we have 1 to 6. The next question is saying that we should find x such that x plus 2 is greater than or equal to 7. So what will I do? This is the condition. So I'll just take out the condition and say x plus 2 is greater than or equal to 7. So what I can do is I can calculate like terms. So I have 7, I have 2. Let me carry this. If I carry plus 2 to the other side, that will turn to minus 2. So this will be x is greater than or equal to 7 minus 2. So I'm saying x is greater than or equal to 5. If I list out all the elements of x such that x is greater than or equal to 5, what will I have? Remember, there's an equal to here. So I will have 5, I will have 6, I will have 7, I will have 8, I will have 9, and I will have 10. Because my universal set stops at 10. So from numbers 5 to 10. Let's see if we're correct. Great. So the next one is saying x such that x minus 2 is equal to 2. Remember, this is the condition. The condition part is after the colon. So I'll just take out that condition part and say x minus 2 is equal to 2. If I carry this minus 2 to the other side, that will be x is equal to 2 plus 2. So what's our x? Our x is equal to 4. So they're telling us that x such that x is equal to 4. So if I replace this with the real value that is meant to be here, what I'll be having here will just be what? Will just be 4. Let's see if we're correct. Great. Now this one is saying x such that 3x minus 2 is equal to 19. Do you want to pause the video and try it out yourself? Welcome back. Let's solve it together. So that will be 3x minus 2 is equal to 19, right? Which can be written as saying 3x is equal to 19 plus 2, right? So 3x is equal to 21. If I divide both sides by 3, my x would be equal to 7. So at the end of the day, when I resolve all of this, my x is equal to 7. So that means in the set that I'm looking for, my x is just what? It's just 7. Let's see if we're correct. Great. And the last of them says x such that x is a factor of 24. If you remember when we were doing LCM and HCF, we talked about finding the factors of a particular number. And then there was a trick we used. We said, if I want to find the factors of 24, I could say 1, 24, because 1 times 24 will give me 24. 2, 12, because 2 times 2 will give me 24. 3, 8, because 3 times 8 will give me 24. 4, 6, because 4 times 6 will give me 24. The next one really will be 6, 4, but that will be like me repeating myself here. So whenever I get to repetition, or I get to where the numbers are the same, something like maybe it was 25 and I get to 5, 5, and then I will stop there. So out of all these numbers, which of them is less than 10? So all of these numbers passes. So if I wanted to replace this, I would say this is 1, 2, 3, 4, 6, and 8. These are the numbers that are within the frame of our universal set 1 to 10. So if you find the numbers x such that x is a factor of 24, we'll be having the values 1, 2, 3, 4, 6, and 8. Let's see if you're correct. Great. 1, 2, 3, 4, 6, and 8. So with this, we've actually come to the end of set builder notation. In the next video, we'll be talking about the laws of sets. So there's some laws of sets. I think there are about 7 laws of sets. We'll be talking about them in depth. See you in the next video.